we are going to spend this entire discussion talking about clouds and how they form. Now, you might be thinking, why clouds? Who cares about clouds? What's significant about that? Well, when it comes to weather, if you have clouds, it means that the atmosphere around you is doing interesting things. So the weather could potentially dramatically change. Obviously, it can't rain or snow if you don't have any clouds. But it's more than just precipitation. It means that several different things are actually going on with the air, things that we can't see because the air is invisible. But the clouds allow us to understand a little bit about what's going on. So let's get started. Water vapor is influenced by heat and air pressure, and changes in temperature or pressure, usually we get both, can cause water vapor to condense into cloud or fog, dew, droplets, rain, etc. When we compress things, that causes their energy and their temperature to increase. Expansion allows particles to cool. So there's water vapor everywhere in our atmosphere. It's in the room that you're in right now. If you go outside, it's right there. So why aren't there any clouds sitting right out where you are? And meanwhile, the clouds are up high where the atmosphere has thinned out. So there are some physical processes that go on that lift up the water vapor up there to where the clouds are. And that's what we'll be focusing on here. So we have these things called adiabatic temperature changes. As you go up in elevation, the temperature gets colder. So it's not like you lose energy as you go up. What's happening is the heat of the atmosphere is spreading out over a wider area because the air gets thinner up there. And this natural change in temperature is called the adiabatic temperature change. When air is allowed to expand, it cools. When it compresses, it warms naturally. So we're not even talking about adding heat to the system or subtracting heat. We're taking a parcel of air that's a certain temperature and we're spreading those gas molecules out more, and that just makes them colder because they're farther away, they're more spread out, so it's heat drops. When you take water vapor and you cool it down to a certain point, it condenses. We call that point its dew point, obviously. So as we go up in elevation, the temperature changes by about 10 degrees Celsius every kilometer or 1,000 meters. And that's, roughly 12 degrees, or sorry, not 12, 22 degrees Fahrenheit. So that's pretty cold, but a kilometer up in the air is also a pretty high distance. This rate of cooling, we call it the dry adiabatic rate because the air is not saturated. It's not yet at 100% humidity, right? Up where airplane pilots fly, the air is, in Fahrenheit, it can be like, 30 degrees, even if it's, the middle of summer and you're flying across the country or whatever. It's extremely cold out on the outside of those airplanes. And sometimes you can see frost forming on them in the middle of summer, like I said. Okay. Eventually, though, the air that's lifted up in our atmosphere cools to the point where the water vapor condenses. So when you take the temperature down to the dew point, it's forced to do that. Now the air cools down. Now the air cools down at an even slower rate, from 5 to 9 degrees every 1,000 meters. And we call this the wet adiabatic rate because once the temperature changes like that, the air around you is 100% humidity. It doesn't increase to 100% and then keep going above 100%. It maintains right there. Now, why does the air cool down at a slower rate? Well, let's look at this graphic just because it's nice. So we start 32 degrees Celsius, which is pretty warm. That's at least in the upper 80s, maybe the low 90s. You can see it cools down. Yep, 10 degrees Celsius every 1,000 meters. And this is just an estimation. It's different everywhere. The reason the cooling slows down up here is because, remember, water is a very good thermal conductor. Air is a terrible thermal conductor. Now, the air up here is still air, but because it's 100% humid, it's laden with much, much more moisture. And that extra moisture is doing an excellent job of absorbing energy, and so it means that it resists having its temperature cooled down, right? So way up here where the temperatures are much colder, the temperatures are much more stable over these vertical distances as opposed to way down here. So here's some clouds. Sorry, I didn't know this picture was going to be up here. And the key to this is if you look at them, and this is true any time of the year you go outside and look at clouds, you'll notice that the bottoms of them, the tops are all fluffy and random shaped, but the bottoms are actually cut off flat, almost perfectly. So it's as if there's this glass ceiling, and all these clouds are kind of on the same level, and they just disappear over the horizon, right? So this flat bottom right here represents the exact point where the dew point is reached, and then above there we have 100% humidity. So exactly what you see happening here. Flat bottoms, clouds over the top. All right, so with these clouds, the moisture, the water vapor was pushed up there where it could condense because it's not just rising on its own. Normally, that high up in the air, there isn't enough water vapor to regularly form clouds. Otherwise, there would just be clouds over the entire sky all the time, and clearly that doesn't happen. There are some parts of our planet where it is cloudy most of the time for certain reasons, and there's other parts of our planet where it's almost never cloudy at all, ever, for different reasons. So now we're going to cover what it is that's pushing up the water vapor into the sky. So how does that saturated air get up there? The first is from mountain ranges. So the wind, especially if you live on the coast, can push air up the slopes of mountains, and then as that air rises up, it cools down. Its water content stays the same, but its humidity keeps increasing and increasing because of the dropping temperatures, and then eventually it forms clouds. Now, oftentimes, as this happens, the cloud dumps out its water content, and we've talked about rain shadows a lot before. Here's the Himalayas. So on the left, we have a tropical rainforest. On the right, we have a gigantic desert, right? Because the clouds never make it over that mountain range. And here on the coast, you can see these pretty low-lying clouds. These hills are not really all that tall. So we have relatively low-forming clouds because where you have the coast, the air is going to be much, much, much more humid, or at least saturated with much more water vapor than in other places. So it doesn't have to rise very far in order for that cloud to form, right? Next is frontal wedging. So a weather front. A front is what happens when two air masses that are different temperatures collide with each other. And it's a big deal when they collide with each other because they're different densities. They start mixing around quite a bit, right? So the warm air always lifts over the cold air. But as that happens, remember, of these two fronts that are colliding with each other, the warm one is going to have more moisture in it because warm air holds more. So as it's lifted up over that cold front, it goes to the higher elevations, it reaches its dew point, it condenses, and then oftentimes these are when the big rainstorms in the summer form, right? You have this really nice summer day, and then all of a sudden a cold front moves in, clouds lift up, and it rains towards the end of the day, right? You can have two air masses that are the same temperature, but in that case, we just call it convergence. So if two air masses collide, they have nowhere to go but up, and so they do. And as it goes up, like in every other example, it rises, cools, and condenses. You don't have to write this down, but this happens in Florida because it's a peninsula, and, well, I just have a picture, so I'll show you the picture in a little bit. And then lastly here, there's this thing called localized convective lifting. So on the surface of our planet, we've talked about this before, different regions heat up at different rates. So some places, maybe there's not a lot of vegetation and the ground gets much hotter. Whereas if you have like a lot of grasses or trees, the ground stays a little more cooler. Well, the hotter ground is going to evaporate much more. And so you can get these sort of isolated pockets where the air is just sort of lifting up in one sort of almost like centralized region. And then that can cause clouds to form over top of it. So in the last chapter, we talked about how if you live on the coast, you may live on the windward side, which means that the the wind blows towards you. Well, on the Florida Peninsula, it just so happens that both sides of the coast, the air rushes or the wind blows towards land. So that's what causes all the uplifting. It's really cloudy and it can rain a lot in Florida. The European continent is sort of like a peninsula. It's fairly narrow. It sticks out into the sea, and so there are some parts on the coast where it rains really a lot. And this is trying to demonstrate localized convective lifting, right? One part of the ground is just heating up more than another part. We know that heat rises, but the other thing about our atmosphere is as you go up, the temperatures decrease. So we have two different things sort of working against each other, right? The air closest to the ground is the warmest, it wants to rise, but the air above it is colder, so it doesn't necessarily want to mix with that air. So stable air is when it matches its surroundings. On a calm day, the air is relatively stable, and there really isn't much mixing of the layers in our atmosphere, right? And we're not talking about like the stratosphere. We're sticking just like in the bottom 3, 4, 5 miles of our atmosphere. So way, way, way down on the bottom. And again, the less the temperature increases with height, or the slower the rate of changes of temperature, the more stable it is. Now, these aren't all that common, but the most stable our temperatures are is when there's a temperature inversion. So that's when it gets warmer as you go up with altitude. Again, it's not very high. We're talking about like go up maybe 1,000 meters and the temperature gets warmer. These temperature inversions really happen as the sun sets because, again, the ground cools down pretty quickly and air is a bad conductor. So that air that's high up, that isn't next to the land, which can change its temperature by means of like conduction and radiation and things like that. That's what causes these temperature inversions. So like what you see on the right here. And that's also what causes a lot of smog in big cities because the pollution can't lift up through the air then like it normally does. So it comes back down and you just get kind of inundated with your own emissions. More on stability and the weather. So the air is always rising. So there's lots of different ways that clouds can form. But when you have stable air, the clouds occupy a really narrow band in the sky, right? So you might see a lot of clouds, but they'll be really thin, right? So they just won't have much of a vertical component to them. Whereas unstable air means we have lots of mixing through any of the methods we just went over. We have pockets of air that are continuing to lift up. And that's going to, as that air lifts up, it condenses the whole time as it's rising. So this is what creates like the cumulonimbus clouds, right? The really big tall ones. And that's a symptom that your air or your weather is pretty unstable, and unstable weather oftentimes leads to precipitation. So we see these rainstorms and snowstorms and things like that when this happens, and hailstorms as well. So here's the same picture from before. And again, this is stable weather. So yes, we have lots of clouds, but if you look, they're all narrow. They occupy a very narrow band in the sky. So this tells us that the air is not churning and mixing and convecting up and down. It's just kind of hanging out in one spot, right? Whereas here, these clouds could be 2 or 3 miles tall for all we know. It actually looks like a fire off in the distance, but they're just clouds. So we have a huge amount of lifting that is going on, right? So that's very, very unstable. And if you look around, it's a summer day. It looks fairly nice out, but later on that night, probably saw a lot of rain where this happened to be. Okay. So the cloud won't just form no matter what. It has to meet two conditions. One, it has to cool down to its dew point, and that just happens naturally with elevation. And the air must be at 100% humidity. So all around us in the sky is the dew point, right? High up, the whole planet covering its whole surface at a certain elevation in the atmosphere, there's the dew point, right? But there might not necessarily be enough moisture in the air for any clouds to form, or it can be so spread out that you just don't ever see the clouds. Maybe the vapor is so thin, or the droplets are so thin that you just don't ever see anything. So we need the 100% humidity also. But another factor that plays into this is water droplets will not just condense on their own. They need help. They need a condensation nuclei, which is any kind of microscopic piece of particulate matter that droplets form around. So the water droplets get a start by clinging on to an object, and then more and more water droplets keep forming around that, right? And these condensation nuclei are extremely small. Like you would need a microscope to even have a chance of seeing them. Very, very, very tiny. But the water droplets are at least 1,000,000 times smaller than they are, right? Because an individual water molecule is just 3 atoms large, so incredibly, incredibly tiny. And the droplets, they're so small that they can just stay aloft in the air for long enough to form clouds.